So in this video, we will be deriving the expressions to calculate for the ideal gas enthalpy for each species as a function of temperature. And how we're going to do this is through Python. And I've already put in a few imports in here. So getting our GitHub CHE tools that we have from other videos we've used as well. And then I imported NumPy, and then we're going to need SciPy root finder, and then obviously the tool CHE. And then I just inputted some of the different like properties that we'll need of different like substances from the question, like methane, ethane, propane, oxygen, etc. And so how we're going to solve this is we have an expression from ChemCAD for our specific heat, and it is this equation 107 right here. And basically what it is defining our specific heat C CP, and it's using the temperature to calculate that. So these coefficients A, B, C, D, and E are all in our CHE tools. Data. So if we look at something maybe for like water, it has these coefficients here. Right here, the heat capacity, it has these coefficients that will correspond to our A, B, C, D, and E in this equation. So what we're going to want to do in order to get a function for the ideal gas enthalpy is we're going to want to integrate that equation that we found, equation 107, from two temperatures, and we are going to be using our standard state temperature of 298.15 to the desired temperature T. So we're going to be integrating this function, and we can split that up into the different addition coefficients here. So we're going to first integrate A, and then integrate B times this hyperbolic sine part here, and then D times the hyperbolic cosine part here. So to start off, we're just going to integrate A. So we're just integrating A with respect to T. It'll just be AT. So we can put that in here. So we're going to want to first just define a function. And we're just going to call it integrate CP. And it's going to be with respect to the temperature. And we're going to want to return it will be A times T. So our A coefficient we're going to get from our CHE tools, and it will be the CPIGA right here, and that times the temperature. So now for the next two parts of the integral, we're going to be using Wolfram Alpha. So we're going to want to integrate and it will be this B times the hyperbolic sine part here. So it will be B times C divided by T, over hyperbolic sine c divided by t, all that squared, like so. And I forgot to put dt. So this will be our answer here, and it'll be the hyperbolic cotangent, which is just 1 over hyperbolic tangent. So that's what we're going to be typing in. So it'll be that plus, put this in parentheses, plus it'll be p dot b times c and all of that divided by b hyperbolic tangent of c over t. And then all this minus or less thing, or plus, excuse me, plus or less thing here. So this will actually be d this time. This will be e. This will be e. And this will be cosine. And we'll run that again. So it'll be, so it is minus will be exponent times this time d and then times hyperbolic tangent. Hyperbolic tangent of, again, this divided by t. Okay, so that lines up, that lines up. Divided by that. minus this whole thing. Alright, so that'll be our integral right here. So there's one thing that messed up here. This obviously is not numpy exponent. I just saw this little e and thought that, but I mean this is our e from here, like the constant e. So these should actually be our p dot cp e. P dot CPE. And then one more thing is that this whole thing is going to be in kilomoles because our CHE tools gives us these constants in kilomoles, so we're going to need to divide the whole thing by 1,000 as well. So now finally we can actually calculate our ideal gas enthalpy, which is the goal for this part or this video. So how we're going to do that is first we need to define a function for the enthalpy. And I'm just going to give us a little bit more space here. Then we're going to define a function for the enthalpy. And what we are going to want to return, or how we're going to calculate the enthalpy, is it will be the heat of formation of an ideal gas. So that's right here, Fig, plus, and what I said in the problem is we will be integrating from the standard temperature and the desired temperature. So what we're going to be doing here is calling our integrate function from above. So integrate Cp at our desired temperature, and then also at integrate Cp also at our room temperature or standard state temperature from our problem of 298 Kelvin. And I forgot a parenthesis right there. So that will be how we will calculate our ideal gas enthalpy, which will be used in our final part of this video where we actually will be solving for our adiabatic flame temperature.